Welcome back to my course. Today we're going to be talking about binary trees. So what is a binary tree? A binary tree is a hierarchical data structure in which each node has at most two children, a left child and a right child. It is widely used in searching, sorting, and hierarchical representations of data. Now let's look at the types of binary trees. There's a full binary tree, where each node has either 0 or 2 children. There's a complete binary tree, where all levels are fully filled except possibly the last level, which is filled from left to right. There is a perfect binary tree, where all internal nodes have 2 children, and all leaf nodes are the same level. Then there is a binary search tree, or BST, which is a binary tree in which the left child contains values smaller than the parent node, and the right child contains values greater than the parent node. Now let's look at the tree data structure. So a tree is a nonlinear data structure that consists of nodes connected by edges. The topmost node is called the root, and nodes without children are called leaves. Now let's look at some properties of these trees. So the root node is the first node in the hierarchy. Then there's a parent-child relationship. And what I mean by this is that nodes are connected through edges, where the top node is the parent and the lower node is the child. Then there's depth, where the number of edges from the root to a particular node, and there's height, which is the longest path from a node to a leaf. Trees are used in file systems, databases, network routing algorithms, due to their hierarchical nature. Now let's look at deleting a node. So node deletion in a binary search tree involves 3 cases. The first case is deleting a leaf node, which is very simple. All you do is just simply remove the node from the tree. Then there's deleting a node with one child, where you would have to bypass the node and connect its child directly to its parent. Then there's deleting a node with 2 children, in which you replace the node with either its in-order predecessor, which is the largest node in the left subtree, or its in-order successor, which is the smallest node on the right subtree, and you delete the replacement node from the original position. Proper deletion ensures that the BST properties are maintained. Now let's look at how to find the min and max of these. So in a binary search tree, the minimum and maximum values are located at the extreme left and right of the tree respectively. So to find the minimum, you start from the root and move left until the last node is reached. Similarly, to find the maximum, you would just start from the root and just move right until the last node is reached. The time complexity of these operations is O to the h, where h is the height of the tree. In a balanced BST, this is O to the log n, but in a skewed tree, it can be O to the n. Now let's look at in-order traversal. In-order traversal is the order in which the nodes are visited. So in this case, they're visited from left to root to right. So first step would be to recursively traverse the left subtree. Then you would visit the root node, and then finally you would recursively traverse the right tree. This traversal technique is used for retrieving sorted data from a binary search tree and has a times complexity of O to the n. Now let's look at a pre-order traversal. So a pre-order traversal follows the root to left to right sequence. So first you would visit the root node, then you would recursively traverse the left subtree, then you would recursively traverse the right subtree. This is used for copying trees and expression evaluation in compilers. The time complexity for this is O to the n. Now let's look at post-order traversal. So post-order traversal follows the left to right to root sequence. So first it would recursively traverse the left subtree, then it would recursively traverse the right subtree, and finally it would visit the root node. This traversal is useful in deleting trees and evaluating mathematical expressions. The time complexity for this is O to the n. Now let's look at balanced trees. So a balanced tree maintains a height close to O to the log n, ensuring efficient operations. Some examples include an AVL tree, which is a self-balancing binary search tree where the height differences between the left and right subtree is at most 1. Then there is a red and black tree, which is also a self-balancing binary search tree where each node has a color red or black to maintain the balance. Then finally there's B trees, which are used in databases for efficient disk-based searches. Balanced trees improve search, insertion, and deletion times, preventing skewed structures. Now let's look at an unbalanced tree. So an unbalanced tree has uneven distribution of nodes, leading to a worst case height of O to the n. This results in degraded search and insertion performance, similar to linked lists. A skewed binary search tree is a common example of an unbalanced tree. Balancing techniques like AVL rotations or red-black tree rebalancing help maintain tree efficiency. Now let's look at time complexity. So the efficiency of tree operations depends on the tree's balance. So for search, insert, and delete, the average case is O to the log n in a balanced binary search tree. And in a worst case scenario, which is often referring to it being a skewed tree or an unbalanced tree, the search time is O to the n. For traversal, it is O to the n of all types, in order, pre-order, and post-order. Balancing trees ensures optimal performance, making them suitable for applications requiring fast lookups and updates. Understanding binary trees and their operations is fundamental for optimizing hierarchical data storage and retrieval in real-world applications, such as databases, AI, and networking. That's all for this video.